So we have additive relationships between the spatial random variables. Actually, I have included that section especially to make a reminder on the previous spatial random variables that we have learned. Because, I mean, it has been too long since we have finished this chapter 5. And basically here we are going to repeat a few topics related to chapter 5. And we are going to explain the additive relationships between spatial random variables. Now, we know that the sum of random variables of a certain type may create a new type of random variable. In literature, for example, we say that the sum of independent exponential random variables, all with the same mean, is called an Erlang random variable. So Erlang is a scientist, is an important scientist who has worked on the queuing theory years ago in the 19th century. So in 1800 years, he has worked on queuing theory. He's an important scientist, but I mean, it's a very, very, I mean, early scientist, let's just say. He was an early scientist and during 19th century, and he has worked in queuing theory. And at that time, the exponential random variable was known. And he has designed a random variable as the sum of independent exponential random variables, but these exponential random variables should have the same mean altogether. And that random variable is called Erlang random variable in literature. Or, for example, when you sum two uniform random variables up, both with the same parameter setting, which means the lower bound and the upper bound parameters are going to be the same for these two uniform random variables, and their summation is going to form a triangular random variable, which is also another random variable that you are going to learn in the future courses, not in this one. But I mean, if you read your textbook, there is always information about the triangular and the Erlang random variable. But I'm not just going to cover them because just by itself, this course is hard enough. I mean, first you need to learn the most important random variables of all, which we have covered in this lecture. And once you have enough knowledge, a solid knowledge on the probability theory and statistics, maybe there will be time for learning these Erlang random variables and triangular random variables in the future, but not just now. Now, among our random variables that we have learned, these kind of summation additive relationships exist as well. So among the random variables that we have learned, we are going to cover each one of them. For example, we know that the sum of independent and identically distributed random variables is a binomial random variable. Okay, we are going to cover that, but first, let us understand what IID means, IID. So in the textbook, in Ross's book, maybe you are going to see this abbreviation many, many times, IID. IID means independent and identically distributed. Now, if the text says that X and I are two random variables which are IID, this means they are independent and their distributions are the same. So they are independent means what? The correlation or the covariance between these two random variables is 0. So this means they are independent. What does identically distributed mean? This means they have the same cumulative distribution function, or in other words, the CDF of f, which is f capital X, is equal to f capital Y for all x values, which means they follow the same distribution with the same parameter setting. For example, if we have two normal random variables with the same location parameter and with the same scale parameter, but if they are independent, then we say that these two random variables are independent and identically distributed. Bağımsız ve özdeş. Türkçesi bağımsız ve özdeş. Independent and identically distributed. But in most of the probability and statistics book, this text uses this abbreviation. Independent and identically distributed is called IID. Maybe we are going to use that abbreviation as well in the future part of our course. So at this point, it is important for you to learn about it. Now, let's just say we have a sequence of Bernoulli random variables, which are IID, which means all of these Bernoulli random variables are independent from each other, and each of them has the same success probability, P. So they are independent of each other, and each xi here is a Bernoulli random variable with success probability P. This means they are independent and identically distributed Bernoulli random variables. So basically, each of these xi values are an indication for the success status of an experiment, whether it shows whether that experiment is successful or is it is failing. Okay. Now, the summation of these statuses are going to count towards the total number of successes, right? Therefore, y here is going to be the total number of successes in an independent experiments. Therefore, y here is a binomial random variable with size parameter n and success probability p, which means sum of independent and identically distributed Bernoulli random variables is a binomial random variable. Now, you know that the expected value and the variance of the binomial random variable were Bernoulli random variable were p and p times 1 minus p. Therefore, the expected value of y, which is the expected value of the sum of Bernoulli random variables, will be equal to the sum of expectations. And each expected value is a p, and we are going to sum these Bernoulli random variables n times expected values, and that is going to be n times p. Similarly, the variance of y is equal to the variance of the sum of these Bernoulli random variables, and that is going to be equal to the variance of the summation of marginal variances for all Bernoulli random variables, plus we are defining the covariances in the covariance matrix, if you remember. And for all dual combinations, we write the covariances and multiply them with 2. But here you see the summation is run from 1 to n and j from 1 to n, which means both the upper triangular and the lower triangular part for that matrix is included here. I mean the green and the blue parts of that matrix. However, it is not important at all because we say that these Bernoulli random variables are independent. All covariances will be 0. So we should not discuss that part. And the sum of the variances will be the sum of the p times 1 minus p values. Because they are identical, they all have the same variance. And the sum of the variance of the sum of the Bernoulli random variables here is going to be n times p times 1 minus p, which is the variance of the binomial distribution. Okay, so you see the expected value of y and the variance of y are the same as the expected value of binomial distribution and the variance of the binomial distribution. Now let's just solve a question. Each time we play a game, we either gain 1 Turkish liras with probability 0.6 or 0 Turkish liras with probability 0.4. What is the expected amount of total winnings in the end of 4 games, it says. So we are playing 4 games. In each game, we either win 1 Turkish liras or 0 Turkish liras. So actually, we have 4 Bernoulli random variables, which are independent. So we assume that they are independent. So how the rounds of a game can be dependent on each other? Every time they have the same success probability. And we have 4 Bernoulli random variables, x1, x2, x3, and x4. These Bernoulli random variables are taking the one value with probability 0.6, so the success probability is 0.6. And the expected value of these Bernoulli random variables are 0.6 for all of them. Now, the question asks me the expected amount of total winnings in the end of 4 games, and that is going to be the expected value of y. Y is the sum of x1, x2, x3, and x4, which is going to be the sum of individual expectations, if you remember. So the expected value of sum is equal to the sum of expectations. And since each expectation is 0.6, the expected value of y is equal to 2.4. Now, if you are, of course, clever enough, and if you are capable of understanding the binomial random variable, without any long explanation like this, you would just say, we know that the total winning amount is going to be a binomial random variable, and the expected value of a binomial random variable is the size parameter times the success probability, and the size parameter here is 4, and the success probability in each game is 0.6. Therefore, the expected value is again 2.4 Turkish liras. Now, I just want to emphasize the relationship between the Bernoulli random variable and the binomial random variable here. Actually, this question is not a typical question that you would see in an exam. This question is just a practical explanation question that emphasizes the relationship between the Bernoulli and the binomial random variable. Now, we can develop a similar relationship between the binomial random variables as well. So let's just say I have two binomial random variables. These binomial random variables have the same success probability P, but they may have a different size parameter. So they may not have the same size parameter. Okay. So X1 is a binomial random variable with size parameter N1 and success probability P. And X2 is a binomial random variable with size parameter N2 and success probability P. Now, what is X1 and plus X2? It is another random variable Y, and it is going to be a binomial random variable with size parameter N1 plus N2 and success probability P. Actually, there is no need for any comment here because X1 represents the number of successes in a Bernoulli experiment sequence where we repeat the same experiment for N1 times, and X2 is the number of successes that we observe in another sequence of the same experiment where we repeat the experiment N2 times. Now, what is the total number of successes? It is X1 plus X2, and that is basically the number of successes in a total repetition of N1 plus N2, and each experiment results with success with probability P. Therefore, the sum of two binomial random variables with the same success probability but different size parameters is also another binomial random variable with size parameter equal to the sum of the size parameters and the success probability being the same success probability. Now, if the success probability were different, then we could not have done this. If the success probabilities were different, then this means these Bernoulli experiments are not identical. Okay? So the success probabilities being different means that the Bernoulli experiments are not identical. For example, one can be taking penalty shots, the other one can be trying 3 points basketball shots. Okay? So because of that reason, we cannot say that X1 plus X2 is a binomial random variable if the success probabilities are different. But here we can say it. Now, once we understand this typical situation, we are going to solve a conditional probability question, which is interesting actually, and it is going to be a long solution. But if you understand this solution, actually, I mean, this is a good thing because, I mean, this means you are experienced enough in probability theory if you understand the solution of this question. It says to a party, 6 men and 4 women are invited. So we invite a total of 10 people, but 6 of them are men and 4 of them are women. Independent of each other, each invited person is likely to participate with probability 0.6. So each person is likely to participate with probability 0.6. After the party, it is thought that 7 people have participated. Okay, so we know that everybody is likely to participate with 0.6 probability. And in the end of the party, we have seen that only 7 people have participated. So actually, we have a binomial random variable here, which consists of 10 experiments, 10 repetitions of the same experiment. There are 10 people. Each can be a success with 0.6 probability, but it says that after the party, it is thought that 7 people have participated. So we have observed that binomial random variable. Now, the question is this. What is the probability that all 4 women were present at the party? Now, we have seen that 7 people have participated. What is the probability that all 4 women were there? Now, that is an interesting question. This question gives me the result of the binomial random variable and asks me specifically that the probability of all 4 women being there. Now, what I'm going to do for this question, I'm going to use my classical modeling approach. Now, if you want to solve these kind of questions, you need to use the modeling with random variables. Unfortunately, that kind of question cannot be logically answered. We need to combine everything that we have learned up to now.